So, last week, we only really got to introduce ourselves to the course and review some fundamental forces. And I say review, but actually a lot of you probably have maybe never had somebody lecture on the fundamental forces. I brought my prop today. So I want to pass this around, and I want you guys to do a couple of things. I want you to feel this attractive force between opposite ends of the magnet. See if you can hold them apart. Feel that attraction. And then I want you to flip it around, and I want you to feel the repulsive force from like ends of a magnet. And these aren't perfect. You know, if you slip them to the side, you can actually feel that attraction a little bit because you've got the opposite ends of the magnets kind of attracting each other on the sides. But hold them there. See if you can't feel that repulsive force. Try to force them apart. Remember that this is my analogy all semester long of what molecules are, of what atoms are. I think I gave you guys that little demonstration that electrons, being charged particles, they spin and create magnetic fields that allow them to pair with another electron that is spinning in opposite way. And that might be an oversimplification of why electrons pair, but it does answer a very good question of if electrons are the same charge and repel each other, why do they always like to be in pairs? So, pass these around, get a feel for that magnetic force because that is chemistry at play, and it's a very good representation of the chemistry that we'll be studying throughout the semester as well. So I want to take a step back. I know you guys are all ready to talk about organic chemistry, but I want to take a step back and just review some very fundamental parts about chemistry in general. So let's talk about the atom. What is the atom composed of? Did we talk about this a little bit last week? Good. All three of the most basic components, protons, neutrons, electrons. What are the two major components of our atom? Quarks. Well, those would be the makeup of the protons and neutrons.
Atom. Sorry, not the fundamental part.
Good. So our nucleus, which is positively charged because it's where all of the protons live. It also has all of the mass. And how big is the nucleus relative to the size of an atom? Yeah, small might be an understatement, right? If an atom was the size of the state of Colorado, then the nucleus is the size of a basketball. So good luck digging into that atom and figuring out where the nucleus is exactly. All the mass, none of the size. Hayden, I think you said then we have the orbitals. And the orbitals can be referred to a little bit differently as well. We can call it the electron cloud, right? And we call it that because it really is just a cloud of electrons. And so, of course, what is the charge around our electron cloud? Yeah, totally net negative. How much mass does our electron cloud have? None of the mass. Some mass, but compared to the rest of the atom, the electron cloud is significantly no mass. But how big is the electron cloud compared to the atom? It is the size of the atom. It's what distinguishes the edge. And our atoms come in a lot of different flavors. So let's talk a little bit about some of those flavors. Real quickly, because I think we did talk a little bit about this last week. Isotopes. Someone got a definition of what isotopes are for me. Good. Number of neutrons vary. The number of protons is what makes an atom a specific element. It's the number of neutrons in that nucleus that changes the isotope. All right. I want to talk about some common isotopes, especially isotopes that we're going to pay attention to a little bit here in organic chemistry. So the first is with our lightest atom, that is hydrogen. The H1 isotope makes up roughly 99% of all hydrogen isotopes. Can you tell me what the nucleus is made up of in an H1 isotope? Just a proton. Because that proton has a mass of 1, and if the isotope has a mass of 1, there are no neutrons. Then a smaller amount is H2. How many neutrons here? In order to be hydrogen, it must have 1 proton, so it has a second mass unit. It's got that neutron in its nucleus. We often don't refer to this as H2. Instead, we give it a different name. This is deuterium. It's not a different element. It is hydrogen, but it's heavy hydrogen. And we can take deuterium and we can turn compounds that have hydrogen into deuterated compounds. So heavy water has a chemical formula D2O. It has hydrogen isotopes that have a neutron in their nucleus. Deuterium is a lot more rare. I want to say it can be synthesized, but I actually have never looked into it, so I shouldn't say that. And it's not the only isotope of hydrogen.
How do you spell deuterium?
Deuterium. It's a good guess. I often get my E's and U's
That looks right.
mistaken though, so I could be wrong. Thank you. Okay, if we call H2 deuterium, then what would we call H3? Tritium. And we often abbreviate it with T. Now, I will be honest, we're not going to deal with tritium here. We will be dealing more so with deuterium a few times this semester, if at all. But there's a lot of organic chemistry material out there that you might stumble across where you'll see D written on a chemical formula. D is not on the periodic table. So it's telling you that you've substituted hydrogen for a different isotope. When you change the number of electrons surrounding a nucleus, we stop calling it an atom and we start calling it ions. Two types of ions, cations and anions. So ions here, the number of electrons vary relative to the number of protons. A couple extra electrons relative to the number of protons, and you get your anions. A few less electrons compared to your protons, and you get your cations. cations are positive. Anybody ever heard that in Gen Chem? I love that one. Always want more cats. Maybe. I've got 3. I'm okay for now. Now, some of you, actually a lot of you, have already submitted your first assignment, analysis of an organic compound. Raise your hand if you've submitted. And raise your hand if I've already agreed to it. No, I haven't. Did I? Oh, I don't remember. Oh, great. Sorry. I must have forgot. I already got a couple of them done. I didn't mean, I really forgot. I felt actually like I was behind, like I dropped the ball. So apparently I haven't. Thank you for that reminder. So how is it that you guys have already submitted your organic compound when we haven't discussed together what an organic compound is? In fact, we haven't even had this conversation about what distinguishes these two terms, molecule versus compound. I'd like to have a little discussion with you guys about the overlap between these and the differences between these. Can we come up with examples that fall into these categories? What's a molecule? What's a compound?
Okay, so like my compound, I chose progesterone because we do a ton of progesterone hormone replacement stuff. It's made up of carbon, which is a molecule of hydrogen, oxygen, and a bunch of those. So that's like the difference, right? Molecule is just more one thing. Compound is all those things combined.
Ooh, okay. I think I heard you say in there that carbon is a compound.
No, it's a molecule.
Carbon is a molecule. I might push back. I don't know that carbon is a molecule. Carbon is an atom
Carbon is an atom.
and an isotope. And I totally blew past the isotopes. Sorry. I was just so hung up on hydrogen. Because I did want to mention, this is organic chemistry, the study of hydrocarbons and their derivatives. And carbon-12 is one of the most abundant isotopes of carbon, but we will also spend a little bit of time talking about carbon-13, and I wanted to just put that on your radar and forgot about it. Sorry. So I'm going to argue that carbon is an atom with different isotopes, but it's not a molecule. It's not. But I like it. And what you said was progesterone is a compound because it's got all these different components. And that's a good basis. A compound has at least 2, so I'm going to say greater than or equal to 2 elements. Otherwise, it's not a compound. It needs to have 2 different components within it. What about a molecule? Will?
A molecule, maybe it's like the simplest form of something that, like, if you put multiple pieces together, it could be considered a compound. But like for the molecule, that I always think was like water. Like it's like a combination of atoms that can't really be broken down into simpler parts without it just becoming individual atoms.
So I'm going to put, we're going to put a definition here, and I'm going to put water as an example. Do you think that water is a compound as well? What do you guys think? Water a compound? Does it have more than one element? It is. Yeah, it does. So I agree, because you can say, I want a molecule of water. No one would push back on that. That sounds like you're using molecule correctly. But then I also want you to consider the compound of water, because it has more than one element.
Yeah.
So I think there's an overlap between these two words. All compounds are molecules, maybe. We'll talk about some examples. But maybe not all molecules are compounds. What else do you think we could say about molecules? How else could we try to define it?
You have 2 or more atoms.
Good. Has at least 2 atoms, two or more atoms. So can you give me an example of a molecule that has at least two atoms but is not a compound? Oxygen gas, hydrogen gas, these are great examples. So to this point about carbon being a molecule, you may be able to argue that diamond is a molecule because there is more than one carbon atom bonded together. But I don't know if anyone would say carbon or diamond is a molecule. I think it's easier to call it a mineral. And minerals aren't often referred to as molecules. I don't know if I said this last week, but I've been saying it a lot. Chemistry, nature, is a spectrum. And we have come in to try and put our nice little lines everywhere and put things into boxes, and nature doesn't care what boxes we've created. So it could be that diamond is an example where it doesn't feel like a molecule, but our box is just not big enough for it, yeah? Okay, what about more examples of compounds? Just a couple more. I'll put progesterone on there, but only by name, because I don't know its chemical formula.
I use hydrogen peroxide in lab today.
Hydrogen peroxide, that's great. H2O2, another compound. All right. I think there's another definition about compounds that has evaded us in this conversation, which is ionic compounds, right? Sometimes ionic compounds have polyatomic ions within them. So we can talk about ammonium chloride, NH4Cl, which is made up of NH4 plus, Cl minus. And NH4 plus might be considered a compound on its own because it is also made up of more than one element, more than two elements. So this feels a little bit like Inception, right? Ammonium chloride is a compound of a cation and anion, where the cation is also a compound of nitrogen and hydrogen. We can make it even more simple though, because we can have something like sodium fluoride, NaF. Now this is a compound because it's made up of more than two elements, or made up of two elements. But if you separated those ions, they wouldn't be compounds or molecules. They would just be ions. You guys agree? So the definition of compound, a little confusing, sometimes a little inception going on, sometimes not. Ionic compounds, covalent compounds, but also covalent molecules. Some covalent molecules are covalent compounds. Some covalent molecules are not compounds at all. So, just some terminology review. I want you guys to be aware of all these little boxes your chemistry professors have been trying to get you to understand. Now let's see where organic chemistry comes into this. Organic chemistry is the study of hydrocarbons and their derivatives. So a great chemist once said, if organic chemistry is the study of hydrocarbons and the derivatives, inorganic chemistry is the study of everything else. And they were right. In fact, all of the general chemistry courses that you took leading up to this, they're often considered like beginner inorganic chemistry. Even though some of you probably saw some organic chemistry in those classes, but you weren't studying predominantly hydrocarbons. Even intermediate and advanced inorganic classes heavily rely on organic chemistry because hydrocarbons and their derivatives are all over the place. So I want to give you guys some examples of these hydrocarbons and their derivatives. Some you'll be familiar with. This is methane, CH4, natural gas. This is acetone. That's a C in the middle. Double bonds. You guys might notice I'm abbreviating part of its bonding structure. I'm saying that there are these groups of 3 hydrogens bonded to each of the carbons on either side. That's acetone. Some of you may know acetone as nail polish remover. What other organic compounds can you guys think of? I know you're thinking of some. Okay, this is a good one. Who said that? No? No? Ellen? CO2? This is a good one. Because CO2, in my opinion, blurs the line. So CO2 can be produced by organic compounds. In organic chemistry 2, you'll learn about a reaction called decarboxylation, where a carboxylic acid group gets heated up and kicks out CO2. So that makes it seem like it's a derivative of an organic compound. It can be produced by an organic compound. But there's no hydrocarbon nature to it. There's no hydrogens on it at all. And so whether CO2 is a hydrocarbon or a derivative or not is not well understood. Again, there's the whole spectrum of chemistry, and we've tried to define these arbitrary lines in the sand. And nature doesn't really care what we've said. So I will be honest, I'm not sure where to put CO2. And there's another compound that is similar. If you take CO2 and you react it with H2O, you get carbonic acid, H2CO3. Now, carbonic acid, I think, is considered a hydrocarbon derivative. We're going to learn about functional groups this semester, bonding patterns within these molecules. And carbonic acid is a dicarboxylic acid group. So a lot of people would consider carbonic acid a hydrocarbon derivative, making it organic. Meanwhile, carbon dioxide, inorganic, even though the distinction between them is an addition of water. Is water organic or inorganic? Inorganic, for sure. And by the way, water can be made from organic molecules as well. Those of you in lab this semester? Oh, a little less than half. Cool. Those of you in lab will be running a dehydration reaction where you take a hydrogen and an OH group off of a molecule and produce water as a side product. But no one would consider water to be organic. Water is definitely inorganic. So, to my point, CO2 can be produced by organic compounds, but is not generally considered organic. Carbonic acid can be made from CO2 and water, both inorganic compounds, and is generally considered organic. It's a weird thing.
This might be a dumb question, but is the differentiating factor between water being organic simply just not that it doesn't have carbon? Like, is that...
Yes and no, because there is a compound called tetrachloromethane, CCl4, and I think that you would consider it an organic compound. even though it's a totally chlorinated version of methane and it has no hydrogens. It's a derivative of that hydrocarbon. It can be produced by it. So, is it the lack of hydrogen? I don't think so. And I don't know that the people who drew the line in the sand knew either. I think they just said, this is what we'll call it, and they didn't think about all the exceptions that would come up. Sure. Good question, Aiden.
So what's the best way to tell them apart? The lack of hydrogen carbon, or like is that like a general rule and there's like some exceptions? Or
I'm going to say 99% of the compounds that have carbon in it this semester are organic. Maybe 1% of the compounds with carbon would be inorganic. I think that's a safe way to say it. There's a compound called acetylene, which is a useful fuel. Anybody that's ever done welding has maybe welded with an acetylene torch. That's got chemical formula C2H2. A fun story about acetylene that is highly flammable is that it can be made by the reaction of water with calcium carbide. Calcium carbide is CaC2. So that's a compound C2 2-. I put it in the inorganic section because it feels pretty inorganic. But again, I don't know. Maybe it is better considered organic. But miners would often take calcium carbide, this hard rock, they'd put it into a little container on their helmets, and just above that container would be a water container, and they could loosen a screw and let water slowly drip onto the calcium carbide. The water would create acetylene and calcium oxide, and that acetylene would turn into a gas, and it would leave their helmet, and they could light it as a torch on their helmet. So they could take this mineral, drip water on it, and get fuel out of it. Very cool. Do we have any other ideas about things that are organic versus inorganic?
I've always been curious about this. Are RNA and DNA organic molecules?
100%. Yeah. RNA and DNA, all of your proteins, even hemoglobin,
Yeah.
which has iron bonding to nitrogen, organic with a touch of organometallic chemistry. But definitely, I mean, you are 90%, maybe less than 90. Water is 70% of your mass, so you're like 30% organic. No. Do I have that wrong? Water is 70% of your body mass?
Like 60 to 70, somewhere in there.
Okay, that's weird. That's a lot. I guess the reality of how big that number is just hitting. All right, well, I'm going to put up some things on the board. What I'd like you to do is work with your group to determine whether these are organic compounds, inorganic compounds, organic ionic compounds, or inorganic ionic compounds. Feel free to take a second to copy them down, but otherwise, start chatting with your group about what could fall into organic molecule, organic ion, inorganic molecule, inorganic ion. I'm gonna steal you real quick because I don't think I got your name. Sarah. Nice to meet you. What's your career path? Digital school. So oral surgeons get in through dental school. Okay. You have to do both. That's a long route. Good for you, Sarah. Any fun facts?
Yeah, that's pretty amazing.
Very cool. You speak Farsi? Good? Yeah, that's cool. I'm learning Arabic. It's hard. I think I've heard that Persians to what is the hard letters that we learn? You think there's some hard letters in Persian? Like Ayn? Oh, okay. Well, I'm not learning Persian yet. Or I guess I'm already happy with it. Thank you, Sarah. It's good to meet you.
I guess what's
It's a halogen and that's definitely ion.
Organic, inorganic, ionic, or not ionic. So like you could say organic molecule, organic ion. Inorganic molecule, inorganic ion. Yep. Yeah. So I mean, predominantly, can you tell what is organic and what is inorganic? And can you tell what's ionic and what's non-ionic? That's what I'm looking for. Why don't you guys try to wrap up in the next minute or two? Can you distinguish what's organic? Can you distinguish what's ionic?
My question is that ionic? Yeah, because is that an organic ion? I feel like the bromine is supposed to indicate
All right, can we go through these together? I'm going to have each table pick a compound that they want to try and classify. Let's start with this table in the far back.
We'll do C6H6.
C6H6. Is it organic or inorganic?
It's organic.
Organic. And is it ionic or covalent?
Covalent.
Good. Non-ionic. So we could say organic molecule. We could also say organic compound. It's a little confusing. Molecule maybe is the only one that doesn't suggest that it could be an ion. Cool. The last table in the back. Okay? Inorganic ion. Good. Let's come to this double half-filled table.
We'll do sodium bromide.
Sodium bromide.
Inorganic ion.
Inorganic ion. Good. You guys here?
All right, so we were kind of debating. So I don't know what that is, but that big long one in the middle, right? Is that an organic ionic compound?
This one here?
Yeah.
So it raises a good question. How can we distinguish whether something is ionic or not? What rules did you learn in general chemistry about ionic compounds?
So we were looking at the bromine. We were looking at so we know that bromine is a halogen.
Good.
Usually halogens are involved with ionic bonds.
Yes.
So we were looking at we were trying to figure out where that bond would be.
Halogens are often in ionic bonds, but not always. For instance, there's a halogen in 4 of these compounds, and I guess maybe this is giving it away, but only one of those 4 compounds with a halogen has an ionic bond. And we've already labeled one as an ion. So can we remember the rule from Gen Chem that helps us quickly identify whether something is ionic or molecular?
Is it if it has a metal?
Not just if it has a metal, because sometimes metals are neutral, and sometimes metals are metallic. Do you want to try again?
Like a metal that's has a charge.
But it could just be a metal on its own.
Yeah.
What can we add to this, Mel?
If it's just a metal, I was gonna say if it's a metal and a non-metal, is usually.
Does that sound right, Alyssa? If it's a metal with a non-metal, we know that metals don't hold on to their electrons very strongly, and we know that non-metals pull on electrons very strongly. Think about your electronegativity trends. So when you have a metal with a non-metal, it's going to give away its electrons to the non-metal, which is going to create the ionic bond. Do we have, sorry Jackie, you had a question first.
I was just gonna say my Gen Chem teacher said the first 2 with the last 4 was an ionic bond.
That's a good place to start, but then you also have the transition metals like iron,
Yeah.
copper, nickel. Those all make ionic bonds. Copper sulfate, very common ionic compound. So it is a good reference, especially in OChem. We're going to be using a lot of the first 2 rows. Actually, primarily just the first row. But any metal with nonmetals. We should call it ionic bond. Any metals here, Will?
I don't think so. Now looking at it again, I was thinking along the lines of like the hydrogens in there being, I know hydrogens can sometimes also be kind of weird.
So hydrogen is an odd one.
Yeah.
If you guys know your periodic table, hydrogen sits above the group 1 metals, the alkali metals. But hydrogen is not considered a metal because hydrogen could also be drawn over the halogens. If hydrogen has one valence electron, then it behaves like the group 1 metals. If hydrogen only needs one additional electron to fill its outer shell, then it behaves like the group 7 nonmetals. So hydrogen is an odd chemical because it is both a group 1 and group 7 element. So, in terms of electronegativity, hydrogen is more electronegative than all the other metals. So because of that, its chemical properties typically lie closer to the other nonmetals.
Okay.
So we're going to say this is only nonmetals. So that tells us there's a covalent bond with that bromine going on.
That makes sense after the explanation.
So now we've got an organic molecule. Let's do this group up front.
We'll do BR2.
Tell me about BR2.
I said it was an inorganic covalent.
Good. Inorganic, no, I can't say it. Inorganic molecule, inorganic covalent compound.
I said molecule.
Good. Why is BR2 not a compound? Just one type of element. Can't be a compound. We're going to be using BR2 quite a bit this semester as a reagent to produce things like CH3CH2Br. So all the chemicals I've put up here, I put them up because they'll be relevant at some point this semester. Now our middle table here. Mm-hmm.
Oh, my bad. I'll do the long one that I can't pronounce the name of, the
NaOCH2CH3. Don't forget the oxygen.
Oh, well, I forgot the oxygen, my bad. I would say that that is a organic ionic compound because sodium is a metal.
Good. I've got a metal and non-metal, sodium and oxygen, written right next to each other. So there must be an ionic bond. And I've got a hydrocarbon chain, O to CH2CH3. Good. Organic ion. All right, somebody help me fill in the rest of these. HOCH3. Organic, ionic, or molecular? Yeah, organic molecule. KOC4H9.
Okay, so is this one ionic because it's potassium bonded to oxygen?
Good.
Okay.
So keep in mind, hydrogen, sodium, potassium, all in the same row. But when written next to oxygen, only potassium and sodium indicate ionic bonds. Hydrogen does not indicate an ionic bond to oxygen. Do you guys see where you can find confusion in that? They're in the same family, but they don't all make ionic bonds. And that's why we can say hydrogen is not a metal. It behaves more like a non-metal, despite having family members that are metals. KOC4H9, we said, organic ion. Good. Now, one thing about this chemical formula, CO4KOC4H9, I've not told you structure quite as much as I have with the other ones. How are those 4 carbons connected? Where are those 9 hydrogens connected? That isn't clear. That is a formula that we will be expanding on throughout the semester, and we'll use it quite a bit. but it won't be in this form, C4H9. We'll actually look at its structure a little bit more. Okay, last one, HBr. Organic or inorganic? Inorganic. Ionic or molecular? Good. Again, H, we're going to consider a non-metal. So this is an inorganic compound. All right, I want you guys to take a minute or 5 to get up and move around and get your blood flowing again before I sit you down to bore you more. So take this opportunity for a break before we come back in. And if you need pictures of the board, now's a good time. I'm going to start erasing stuff on it. I had a student that took my summer OCHM one, and then he transferred up to the U for about 2 weeks. And he said, I'm feeling confused, can I come to you for office hours? So then he came down, and they teach in a different sequence there. So there were reactions he was expected to know that he hadn't learned yet, and reactions he had already learned that he wasn't going to react. He was going to see again. But ultimately, he sounded like he just couldn't handle what that professor was asking. And I was like, shoot, my goal is to set you guys up with a strong foundation so that if you go to take it with another professor, you have the skills to understand and catch up with what they're talking about.
Like, this review was so nice. Because in the class I took last week, like, we didn't review much. It was like, basically just structure and go over anything else. And it was just like kind of moving on. And I was like, this is going to be hard.
It is hard.
But
It is hard to do that.
yeah.
But it also kind of makes sense because you've got places to be and things to do, and the longer we take talking about Gen Chem concepts, the less time we have to talk about the real challenges. But I want you guys to be at your best.
Yeah. Because, like, it's been semesters.
Yeah.
Taking chemistry.
Sure.
So,
And not just you, right? Some of these people are coming back. How long? How long has it been?
yeah.
It's a long time.
I appreciate it. I think you explained things very well.
Thank you. I'm glad that it's meaningful. Your comment last week was so nice. I went home and told my partner about it. It's okay. It really is. Your sweater is getting a little bit of emo vibes. If it was just a little bit lighter, really be there. Oh. Some word of mouth? Somebody referred you?
Yeah, because
Who? Name one who isn't.
yeah, that's so valid. Somebody took your class. My physiology class.
Oh wow. So it wasn't even a good friend of yours. It was just
Literally just.
wow.
Yeah.
Well, it keeps me in business.
crazy being on the third floor. I've never been up there.
Isn't this such a nice room?
A room with windows is a nice room.
When I passed you in the hallway in the spring,
Yeah.
you were in 092.
It's that end room on.
Like
The
really
right
close
side.
to the door, right?
Yeah. You might
Really
have saw
close to the
me
stairwell.
from by calculus. It was 080.
Oh, you were kind of in the middle of the hallway.
Yeah, I'm there and the last classroom on the end. I was taking.
Not the one, not the classroom closest to that. The classroom closest to the hallway.
Yeah.
So I'm teaching in that room the first time this semester.
Oh yeah. It's
092. It's a big room.
Yeah. Those rooms are
Huge.
huge.
No windows. These windows are kind of nice because we'll get to watch sunset.
Yeah.
Or I will. You guys are looking this way.
I'm like, oh, send that. Everyone take a break and we'll.
I don't know. I wouldn't do that. But I do often in labs. I stop people when I see an airplane shadow.
An airplane shadow.
The airplane shadows. You know the airplanes follow the 215 and Bangor down to the airport.
Okay.
And so the airplanes fly right over Slick, and at the right time of day, their shadow falls on the SI building. And then it moves across campus. But that means usually in the afternoon, the planes coming in will cast their shadows over the lab windows. And so you get this like flash of dark. And I'll go, airplane shadow. I love it. I get distracted by it.
Yeah.
But it's fast enough that if you're not paying attention, you miss it. All right, guys. Welcome back. So, formal charge is an incredibly important concept. We talked about some charges in there. I know some of you are familiar with how to calculate charge. Others of you maybe have forgotten. So, formal charge, or FC, can be calculated from a Lewis dot structure by taking the number of dots, by taking the number of valence electrons for an atom and subtracting the number of dots that surround it. Remember that dots in Lewis dot structures represent electrons, and the number of bonds that connect it. So some textbooks will say the formal charge is valence electrons minus non-bonding electrons plus half of the bonding electrons. Well, half of the bonding electrons is the number of bonds. 2 electrons to a bond, so you just count the bonds. You don't have to divide by 2. So this is our equation for formal charge. Last fall, a year ago, was the first time that I ever taught OChem 1. I've been teaching, Gen Chem 1. I've been teaching OChem for a long time. So I kind of forgot how general chemistry students learn about formal charges. But when I read the textbook, it said formal charge is a bookkeeping method. It doesn't necessarily say much about charge. And that shocked me. I wasn't expecting it to say formal charge is a bit arbitrary. It's just for bookkeeping. Because formal charge has real life implications. For instance, the magnets I passed around earlier. When you've got something like an anion, that anion is oftentimes located at a specific atom that creates a high density of negative charge that allows it to be attracted to high density of positive charge. So I don't know if I believe that it's just a bookkeeping. In my opinion, formal charge is telling you about your magnet. Is it a negative magnet? Is it a strong magnet? Sometimes formal charge can actually be distributed across several atoms, which at each atom is going to weaken it as a negative magnet. So this is the way that we calculate it. But I would rather you get familiar with common bonding patterns and formal charges so that you can crank out lone pairs or non-bonding pairs quickly. Or vice versa, if you have lone pairs, you can crank out the charge quickly. So together, I want us to build a table. Along the top of this table, and if you're doing this in a notebook, make it big. Take up a lot of space. Give yourself room for this. Along the top, we're going to have some of our key players this semester. Carbon, nitrogen, oxygen. X represents halogens. So if you want to pick a specific halogen, the most common ones we'll use are chlorine, bromine, and sometimes iodine. Carbon-fluorine bonds are very strong, hard to break, so it's rare that we will explore fluorine as a halogen. Vertically, I want us to have a +1, a neutral, and a -1 row. So we're going to build this table, and we're going to look at all of the most common bonding patterns that give us these formal charges on our key players. Boy, my box is not doing very well. All right, starting with carbon. Carbon likes to make 4 bonds, and that's because it has 4 valence electrons. So if I have 0 dots and 4 bonds, I get 4 minus 4. So neutral carbon likes to have 4 single bonds, 2 single bonds and a double bond, 2 double bonds, 1 on either side, or 1 single bond and 1 triple bond. There is a bonus bonding pattern for carbon, and we will see it this semester. That is when carbon has only 3 bonds, but it holds a lone pair. It holds a lone electron, not a pair. Unpaired, non-bonding electron. Notice 4 valence electrons for carbon minus 1 dot and 3 bonds, 4 minus 4. Can you guys remind me what an atom with an unpaired electron is called? Or a compound with an unpaired electron? Notice the charge. It's not an ion. It's highly reactive. I don't know if that gives it away. I think Belen might have had it. This is a radical. So if you've ever heard about radicals in any other context, this is what it's likely referring to. The radical is the unpaired electron. And that then propagates to the whole atom. That atom is now a radical. That propagates to the molecule. The compound is a radical. I learned a little bit about radical. Radical means from the root, like the most fundamental, which is why in math, the radical symbol is the root symbol, because it emphasizes what it comes from, the root of it, the radical of it. When you apply radical to people, you're saying like, oh, they're so radical because that's coming from a fundamental kind of like mindset. And here, I think the term radical applies to an unpaired electron because how much more fundamental does it get than just one electron that doesn't have a pair? So that's the root of all bonding in chemistry. The radical is the unpaired electron. Cool. No charge, neutral, highly reactive. Now, carbon with a positive charge. This happens when carbon has 3 single bonds, but is missing its filled octet. Notice that that is 6 electrons around carbon, 4 minus just 3 bonds, plus 1 charge. The other common way that this happens with carbon is when it has 1 single bond and 1 double bond. We're going to talk about hybridization. We're going to talk about geometry, not just yet. But I want you guys to be able to come back to this conversation about charges and actually think about what is the hybridization at these atoms? What is the molecular geometry at these atoms? We'll get there, but I want this table to be a resource you guys come back to. Carbon with a negative charge. Similar to these instances, the only difference is carbon with 3 bonds holding a lone pair. So that can be 3 single bonds with a lone pair, a single and a double bond with a lone pair, or a triple bond with a lone pair. Notice in the equation that that gives you 4 minus 2 plus 3. 4 minus 5 is negative 1. That's a really bad triple bond. But those are your most common bonding patterns where carbon holds a negative charge. All right? Now, what I would like you guys to do is expand this to nitrogen, oxygen, and the halogens. Actually, I'm gonna give you the halogens as well. Here's why. The halogens can often expand their octets. Chlorine, bromine, and iodine, they're all in row 3 or lower, which means that they can take on more than just an octet, but they're not going to do that in our organic chemistry courses. So here are the bonding patterns that you'll see for halogens. A halogen with 2 bonds and 2 lone pairs holds a positive charge. There are 2 ways that that can look. 2 single bonds or 1 double bond. A neutral halogen either has just 1 bond and 3 lone pairs, or it has 3 lone pairs and a radical. And then lastly, a negatively charged halogen has 4 lone pairs. So I want you guys in your groups to try and propose bonding patterns for nitrogen and oxygen that satisfy their +1 neutral and -1 formal charge states. I can tell you that you're not going to have more than 4 possibilities. So if you feel like you're coming up with a lot of wild ideas, maybe rein it back in. And again, this is hard because I know the common bonding patterns. You haven't spent as much time with it. But this is your ABCs. This is what you'll be seeing all semester long, and I want you to be familiar with them and recognize them quickly. I'm going to give you a hint. These atoms become more electronegative as you go to the right along the periodic table. They are all in the same row. So, atoms to the right prefer to have more electrons to themselves. So a negatively charged carbon is what a neutral nitrogen looks like is what a positively charged oxygen looks like. This row, this diagonal looks very similar. And then similar with this diagonal, and, well, that diagonal doesn't actually exist. But similar with this diagonal. The positively charged halogen is what a neutral oxygen looks like, is what a negatively charged nitrogen looks like. As you get more electronegative, you want more electrons for yourself. As your valence shell fills more, you want more electrons for yourself. And so I want you to look for that pattern as you fill this in with your group. Spend about 10 minutes working on this together, please. Mm-hmm.
So nitrogen has, yeah, so it needs to be more. Yeah, that makes sense.
Just ignore the radical. I would encourage you to not attempt with radicals. I will tell you the radical ones. Because radicals are strange. How what? Yeah. Here's a tip. These bonding patterns in carbon are going to result in a positive charge nitrogen. Just don't forget to show your positive charge. So copy those bonding patterns, but make it nitrogen. Good. 5 valence electrons minus how many dots surrounding the nitrogen? Well, here there's 2 dots surrounding carbon and 3 bonds. This has good 0 dots plus 4 bonds. 5 minus 4 plus 1. Good. Any looking less than? That's okay. It's good actually. It's the right radical. As long as this is a bond. Yep. Good work. Don't forget the negative charge here. But I think it looks great. Are you working with anybody? The only thing I'll ask for, Aiden, is show your charges next to those.
Oh, okay.
Next to those atoms.
Okay.
Charges
so far
then
then in terms of
I think this looks like this. Oh, this is a radical.
yeah.
Actually, I would put in it because I don't think it's wrong, but it's not likely to exist. You did the right idea where you just copy and paste.
Yeah, because I was like,
But I would avoid it. Yeah. So far, so good. Oh, it's not wrong though. Oh, well, actually, you have 4 lone pairs, so 8 total electrons. So I think that gives it a 2 minus charge. There would be 6 valence electrons for oxygen, minus 2, 4, 6, 8. 6 minus 8, negative 2. Yeah, or I would just ignore it, because you won't actually see O2 minus in OChem. You'll see oxygen bonded to carbon very often and bonded to hydrogen very often, but you won't see it O2 minus. It's like its most oxidized, most reduced form. You could just erase the whole thing, just because it won't be relevant. The one that you have there is the minus. That's clever, dude. Work smarter, not harder. My boxes are a little weak. So Jason, if I can say anything, it would be just to add your charges next to the atoms. I know they're in that row, but I want to emphasize you guys know.
Yeah, so the problem is saying like the way that I'm surprised so far to see if I got my understanding correctly. So if you take the neutral nitrogen and it becomes +1 if you remove the lone pair. So it becomes -1 if you turn one of them. If you turn one of them on.
I'm gonna get it.
So wait, neutral oxygen is okay, I'm starting to get this. Yeah, I see.
It can make less, it can make more. At maximum, it can make 4 bonds. Because
Okay,
this
so I see the pattern. You add O beyond pairs to make the word like 5.
So it likes to make 3. Neutral. But it can make 4. Take for instance, not up there. Ammonia. There's a lot of organic compounds too that are they're methyl ammonium groups, and so you've got the nitrogen coming off the carbon chain, and then it's got 3 other carbon chains coming off of it, and it takes on a I'm not gonna get there. Good work. All right, guys, we are in our last 10 minutes, so I want to make sure that we have time to wrap this up so that you don't have to bring any questions home. But I do want to say, sometime this weekend, maybe set a reminder. Try to build this table again from scratch. Don't look at it. Just remember as much as you can, and then compare it. These are your ABCs. This is the building blocks of our molecules this semester. And so it is important that you can look at a bonding pattern and figure out what charge needs to be there. And look at a bonding pattern with a charge and figure out how many lone pairs are there. Because for most of the semester, we'll be assuming lone pairs. They just get a little too tedious to draw. You are allowed to draw them, but a lot of your materials will not show them. So these are your ABCs. Get to know them. Repeat this little exercise as many times as it takes to say, I know all the different ways carbon can bond and take on these 3 different charges. Deal? So I mentioned try to avoid radicals in this. If we take these other 4 bonding patterns at carbon and we replace it with a nitrogen, that nitrogen takes on a positive charge. I do want you guys to show charges. So even though these are all in the +1 column or +1 row, I want you to show formal charge. That is something that we will never be assuming throughout the semester unless I am assessing you on your ability to figure out the formal charge, in which case I have to show you all of the lone pairs. So it's kind of a give or take, and we'll talk more about that agreement later. I said earlier the negatively charged carbon looks like the neutral nitrogen. Nitrogen likes to have a lone pair for itself. Nitrogen can also have a lone pair and a radical and take on a neutral charge. This is not as common. So if you don't want to memorize that one, don't worry, you're probably not going to see it again. A negatively charged nitrogen actually looks like a neutral oxygen. This is when nitrogen has too many lone pairs for itself. This happens when nitrogen takes on 2 lone pairs and only 2 bonds. Replace that nitrogen with an oxygen, and you've got your 2 neutral bonding patterns for oxygen. In addition, and this one is a little more common, oxygen can have 2 lone pairs, 1 bond, and 1 radical. We will show that at least once this semester, but probably not with the nitrogen. A positively charged nitrogen means it doesn't have enough electrons for itself. A positively charged oxygen looks like a neutral nitrogen. 3 bonds to oxygen in any of these combinations gives it a positive charge. A negatively charged oxygen, there's really only 1 bonding pattern for this. That's when oxygen has 1 bond and 3 lone pairs. To quickly apply this information, I want you guys to draw some formal charges on a few structures. This compound is called azide. I'd like you to figure out the net charge on azide and the formal charges within azide. This other compound is called the tert-butyl or T-butyl cation. No lone pairs shown because no lone pairs are present. I'd like you to figure out the net charge there and the formal charge there. So by the way, for those of you in the back, this is CH3, 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 all bonded to C. talk with those around you about the formal charges that you decided on. Do you agree? Do you disagree?
For the other one. Well,
Good thing. All right, you ready? What's the net charge on azide? -1. This can be written as N3 minus. Actually, the name kind of indicates that to you. IDE is a common suffix in nomenclature that indicates something being negatively charged. The nitrogens on the outside both have negative formal charges. You can see they both look like this. And the nitrogen in the middle looks like this nitrogen has a positive charge. On the tert-butyl cation, +1. Cation should be your hint there. And which atom is it on? Carbon in the center. You'll notice that these carbons on the outsides, they all have 4 single bonds. 3 to the 3 hydrogens, 1 to the carbon in the middle. But the carbon in the middle only has 3 bonds. That gives it that positive charge. These are some common things that we'll be seeing. The last ones that I want to ask you about are this oxygen and this oxygen. Can you tell from these condensed molecular formulas what their formal charges are? When I expand HOCH3, I can actually show the bonding, the covalent bonding between oxygen, hydrogen, and carbon. Now it must have those 2 lone pairs on it as well, and that means I've got an oxygen in this type of bonding environment, neutral. But when I look at NaOCH2CH3, I knew that Na is Na plus because I've got a metal and a non-metal. So something must be negative. But oxygen is covalently bonded to carbon. To have an octet, that oxygen must have 3 lone pairs, which means my oxygen looks like this bonding environment. So where is the negative charge that balances Na plus? It's on the oxygen. CH2 has 1 bond to carbon, 1 bond to oxygen, 2 bonds to hydrogens. Carbon is neutral. Both the carbons are neutral. Oxygen is in a negatively bonded environment, which is why we write NaO. They indicate that they are the ionic pair by being written next to each other. So again, you do have real homework. Active is ready for you. But your exercise this weekend is to try and build this table from memory. And then do it again. And then do it again until you feel like these are your ABCs and you've got them down pat. Deal? Have a great weekend, guys. We're going to keep diving into section 1 next week.